Poisson rate tests. Poisson rate tests are statistical methods used to compare the frequency or rate of events that occur over a fixed time, space, or unit, especially when the events are rare and independent. Based on the Poisson distribution, these tests are useful for analyzing count data such as defects, accidents, or arrivals, and help determine whether the observed difference in rates between two groups or between a group and a standard is statistically significant or due to random variation. Welcome everyone to today's session. In this session, we'll explore a powerful statistical tool used in process improvement, Poisson rate tests. These are particularly useful when you're analyzing how frequently events occur in a given time, space, or batch. By the end of this training, you'll have practical, hands-on knowledge to apply these tests in your work. Whether you're monitoring defect rates, service interruptions, or any type of count-based occurrence. Our focus will be on two specific types of Poisson rate tests. 1. Poisson rate test, which helps compare a sample rate to a known standard. 2.2 Poisson rate test, used when comparing rates between two samples or systems. Let's walk through the concepts, applications, assumptions, and how to interpret the results of each test. Let's get started. Now let's understand what Poisson rate tests are and when they are used. When you're dealing with discrete count data, like the number of defects, complaints, or failures, you might want to measure how frequently these events occur. That's where Poisson rate tests come in. There are two types of Poisson rate tests depending on your objective. 1. Poisson rate test is used when you want to compare the observed rate of occurrence in your data to a known standard or historical benchmark. For example, are we seeing more errors per hour today than the standard rate? 2.2 Poisson rate test is used when you want to compare rates between two different samples or groups, like defect rates in two different shifts or two machines. The Poisson process itself is a way to model random independent events occurring over time, space, or any measurable unit, like per minute, per square foot, or per production batch. So, whenever you're monitoring rates of discrete events, Poisson tests help you understand if your process is in control or has significantly changed. Let's explore what Poisson rate tests actually are and when we should use them. Poisson rate tests are a type of statistical hypothesis test used specifically for count data. These tests are ideal when you're dealing with rare or infrequent events that happen over time, space, or other measurable opportunities. For example, number of defects per hour, number of errors per day, number of machine breakdowns per shift. The idea here is to determine if the rate at which these events are happening is normal, or if it's significantly different from a known standard or between two different systems. We use Poisson rate tests in three key scenarios. 1. When we are measuring discrete count data like defects, errors, complaints, etc. 2. When these counts are distributed across time or space, for example, how many breakdowns occur per hour, or how many errors are reported per batch. 3. And finally, to statistically verify whether the event rate matches a target or differs significantly between two processes or systems. Let's explore what Poisson rate tests actually are and when we should use them. Poisson rate tests are a type of statistical hypothesis test used specifically for count data. These tests are ideal when you're dealing with rare or infrequent events that happen over time, space, or other measurable opportunities. For example, number of defects per hour, number of errors per day, number of machine breakdowns per shift. The idea here is to determine if the rate at which these events are happening is normal, or if it's significantly different from a known standard or between two different systems. We use Poisson rate tests in three key scenarios. 1. when we are measuring discrete count data like defects, errors, complaints, etc. 2. When these counts are distributed across time or space, for example, how many breakdowns occur per hour, or how many errors are reported per batch. 3. And finally, to statistically verify whether the event rate matches a target or differs significantly between two processes or systems. This slide introduces the one-sample Poisson rate test, which is one of the two types of Poisson rate tests. This particular test is used when you have count data and you want to compare the observed rate of occurrence against a known target or standard. Let's break this down. When to use. Use this test when you're comparing a single sample's rate of occurrence to a known benchmark. For example, suppose your target is 10 defects per 1,000 units, and you want to check if your current defect rate meets or deviates from that standard. Null and alternate hypotheses. OH0, null. The rate of occurrence in your sample is equal to the standard or benchmark. OHA, alternate. The rate of occurrence in your sample is not equal to the standard. This suggests that the system or process is behaving differently than expected. Example. Let's say your production line is expected to produce 500 units per day with an average of 5 breakdowns. You can apply the one-sample Poisson rate test to verify if the observed rate of breakdowns is still in line with this standard or not. This slide explains the conceptual foundation behind the one-sample Poisson rate test. Let's begin by understanding the purpose of this test. The one-sample Poisson rate test is used when we want to evaluate whether the rate of occurrence of rare events in a given sample is significantly different from a known or expected rate, such as historical data or a target rate. When to use it. This test is ideal when you're counting rare events, like machine breakdowns, error messages, defects, etc., over a fixed interval such as time, space, area, or units. The assumption here is that these events follow a Poisson distribution, which models the occurrence of events that happen independently and at a constant average rate. A common use case is to compare the current performance to a historical benchmark. For example, if your historical rate of machine failure is 5 per week, but this week you recorded 9, you can use this test to determine if this increase is statistically significant. Summary. This test helps in quality control and operational decision-making where benchmarks or standards are in place. It's a useful tool to confirm if a change in rate is just a random fluctuation or a statistically significant signal requiring action. This slide explains the 3 critical assumptions that must be met for the one-sample Poisson rate test to be valid. Assumption 1. Events occur independently. This means that the occurrence of one event should not influence the occurrence of another. For example, if you're measuring machine breakdowns, one breakdown should not increase or decrease the chance of another breakdown in the same time frame. Assumption 2. Events follow a Poisson distribution. The Poisson distribution models rare events that happen at a consistent average rate. It is most appropriate when you're measuring counts of events that are infrequent or happen at irregular intervals, such as defects, phone calls, or failures. Assumption 3. Event rate is constant over the observation window. This implies that the probability of an event occurring is stable across the entire duration or area of observation. So, if you are monitoring calls received per hour, the arrival rate should be relatively consistent throughout the day. Summary. If these assumptions are not met, the validity of your test results can be compromised. It's important to check for these conditions before proceeding with the analysis. In this slide, we'll walk through how to interpret the output from a one-sample Poisson rate test. Let's start with the p-value. The p-value is the first thing to look at. In our example, the p-value is less than 0.05, which is the commonly accepted alpha level. This indicates that the null hypothesis, HO, can be rejected and the alternative hypothesis, HA, is accepted. In simple terms, the test is telling us that the rate of occurrence in the sample is significantly different from the target rate. Now, let's move on to the confidence interval, CI. The confidence interval provides a range within which we expect the true rate to lie. Here, the CI is from 62.3912 to 66.8670. Since the target rate of 70 does not fall within this interval, it reinforces our conclusion that the sample rate is significantly different from the target. Lastly, a tip. If you don't have a predefined target rate, you can still use this test to understand or describe the natural behavior of the population by analyzing the observed rate and its confidence interval. This slide focuses on the two-sample Poisson rate test, which is used when you want to compare event rates between two different groups or samples. Let's break it down. When to use? We use this test when we are interested in comparing the rate of occurrences between two samples. The key here is that we're dealing with count data, like the number of defects or breakdowns, and we want to see whether the frequency of these events differs between two distinct groups. Null and alternate hypotheses. HO, null hypothesis. The rate of occurrence in both samples is equal. CHE, alternate hypothesis. The rate of occurrence in the two samples is significantly different. So, we're trying to statistically confirm whether the difference in observed rates is just by chance or is truly significant. Example. Think about a factory setting where two production teams are working different shifts. We want to compare the rate of daily defects between these two teams to see if one team has a significantly better or worse defect rate. In this slide, we dive deeper into understanding what the two-sample Poisson rate test is and when to use it. What is the two-sample Poisson rate test? This test helps us compare the rate of rare or infrequent events between two independent groups or over two different time periods. It's a statistical hypothesis test, assuming the data follows a Poisson distribution. When to use it? There are three main conditions that indicate this test is appropriate. 1. You're comparing event rates, not just counts, between two groups. This means you're not just looking at how many times something occurred, but how frequently it occurred in relation to time, space, or volume. 2. The events are rare and occur randomly over a fixed interval, like number of breakdowns per machine hour or defects per square meter. 3. You want to test if the difference is statistically significant, meaning the observed variation in event rates isn't just due to chance. For example, this test would be used if you're trying to determine whether two shifts in a manufacturing unit are producing defects at significantly different rates. It provides strong evidence for performance comparisons and improvement opportunities. Encourage your participants to think of scenarios in their processes where rare events happen and where comparisons between two groups or time periods would add value. Two-sample Poisson rate test. Key assumptions. In this slide, we cover the key assumptions that must be met for the two-sample Poisson rate test to be valid and meaningful. Let's break these down. 1. Events in each group are independent. This means that the occurrence of an event in one group doesn't influence the likelihood of it happening in the other. For example, if we're comparing defect rates on two different production lines, issues in one line shouldn't impact the other. 2. Events follow a Poisson distribution. We assume that the events we're tracking are rare and occur randomly over a specified time or space. Examples could include machine breakdowns per shift, errors per 1,000 transactions, or calls per hour in a call center. 3. Event rate is constant over the observation window in each group. The rate of events must be steady during the time or area observed in each group. If the rate changes too much over the period, the results may be misleading or invalid. These assumptions are important to ensure that the conclusions we draw are statistically sound. Before applying the test, encourage participants to check if these conditions are reasonably met in their data. In this slide, we're learning how to interpret the results of a two-sample Poisson rate test using the output of a statistical software. Let's walk through the interpretation. First, focus on the p-value. Here, the p-value is shown as 0.002. Since this is less than 0.05, we reject the null hypothesis, HO, and accept the alternate hypothesis, HA. This tells us there is a statistically significant difference in the event rates between the two groups, in this case, males and females. Next, look at the estimated difference in rates. The rate for males is 65.93, and for females it's 56.42, with an estimated difference of 9.50. That means, on average, males had a higher rate of the event under study compared to females. Also observe the confidence interval for the difference. Here, the 95% confidence interval ranges from 3.43 to 15.57, which does not include 0, further supporting the conclusion that the rates are significantly different. In summary, p-value less than 0.05 significant difference CI does not include zero strong evidence. So, we conclude that gender does significantly affect the outcome being measured. This slide gives us a quick comparison between the one-sample Poisson rate test and the two-sample Poisson rate test, both of which are used when the Y variable is count data, such as the count of production units or defects. Let's begin with the one-sample Poisson rate test. This is used when you want to compare the observed count to a known standard or benchmark. For example, if your production target is 100 units per day, and you want to see whether your actual production count differs significantly from that target. The null hypothesis, HO, assumes the sample rate equals the standard. The alternate hypothesis, HA, assumes it is not equal. In the example, we're comparing production count to a standard to check for any deviation. Next, the two-sample Poisson rate test. This is used when you want to compare two different sample groups, such as two processes, two shifts, or two lines of business, LOB. The null hypothesis, HO, assumes that both sample rates are equal. The alternate hypothesis, OHA, assumes they are significantly different. The example here is comparing production counts between two different shifts or departments to evaluate consistency or performance differences.